One. There we go. Why isn't it counting? There we go. All right, anyway, sorry. So exponential function. So we need to talk about a different type of function than just linear. So let's say we take this example here. Now this example does get a little, there's so many decimals that it can be a bit hard to follow at times. So I'm going to pull up, once I go through this example, I'm going to pull out just off the top of my head another hopefully easier to follow example, but this does illustrate what we're talking about. So we have years and we have population. And so let me first note that all of these, changes in the years go up by 1 each time, right? So if I were to look and see if this was linear. Okay, heard, David, I will take care of that. So all of these years go up by 1. So if we wanted to see if this data was linear, we would essentially just need to care about the change in these populations. So that's why I have this third column here. We're just going to look at the change in the population to see whether or not this data might be linear. So, and I'm going to do it like this to kind of keep track of where these numbers are coming from. So if I look at the change in population from 2007 to 2008, so 14.66 minus 14.235, we're going to get 0.425. And then if I find the change in the next set of years, it's going to be 0.438. Well, at this point, we already kind of know that that's obviously not going to be linear because those two don't match. And since the years all go up by 1, they would have to match. But let me just finish filling it out really quick. Between 2009 and 2010, we have a change in population of 0.441, and then 0.464, and then 0.478. I don't know why I made this table so long, but anyway. So obviously none of those change in populations match. So this definitely wouldn't be a linear function. So something else has to be going on here because there is actually a pattern. It's just really hard to see. And that's what I mean about this example. And I'll pull out the nicer looking example in a second. It's really hard to see the pattern that's happening here. But let's look at the ratio between consecutive years. So we're specifically going to take consecutive years here for a second. So I can't take like 2007 and 2010. But let me take the, so let me say 2007 to 2008. And I was going to put the later population on top in the numerator. So if I take the ratio of those two populations, I get 14.660 divided by 14.235. This comes out to the decimal 1.02985599. And it's lagging. There we go. Well, let me take another set. What about from 2008 to 2009? Well, if I take the population in 2009, so 15.098, and divide it by the population in 2008, I get the decimal 1.029877217. And maybe one more, 2009 to 2010. So 15.549 divided by 15.098. It's going to get me the decimal 1.029871506. Now, notice that while they're not the exact same number, they do agree up to 4 decimal places. And that's not a coincidence. That's the pattern. So no, they don't match perfectly, which is why it would, well, that's part of why it would be hard to see, but it's also hard to see because multiplying a number by 1.0298, no one can do in their head. But essentially what's happening is between all of these years, if we go from one year to the next, the population, if I take the earlier population and I multiply it by 1.0298, I'm going to get approximately the next population. So essentially what's happening here is to get from one y value to the next one, we're multiplying by this number. And again, I know these are all slightly different, but since this matches, since these match up to 4 decimal places, we're going to say it's good enough. So a lot of times with these types of exponential functions, you can run into issues with rounding. So if you think about these populations, they're probably cut off and rounded a little bit since it's cut off to millions and only 3 decimal places. So maybe if we were given the full, not rounded population, maybe it would match completely. But matching up to 4 decimal places is what we'd consider good enough. I would also say up to 3 decimal places is good enough. If you were to be doing these ratios and you were to find something like 1.05 versus 1.03, those are too far apart. Like, we would not say that those are good enough. They have to be pretty obnoxiously close to each other. So you want at least 3 decimal places agreeing to say that it's exponential. But we would say that this set is exponential because these ratios are matching up to 4 decimal places. So that's the kicker, if you will, with exponential functions is we say that this data has a constant factor. So linear functions have a constant slope. Exponential functions have a constant factor. So let me pull out, this is just off the top of my head, and I'll do it in a different color to try to keep it separate. Say we had another set of data, 1, 2, 3, 4, 6, and 2, 4, 8, 16, 64. I think this one, it's easier to see kind of what's happening. If I go from one y value to the next, I multiply by 2, right? To get from 1 to the next, I multiply by 2. To get to 1 from the next, I multiply by 2. Now that doesn't happen in this last set, but notice that we didn't go from 4 to 5, we went from 4 to 6, so we kind of made a jump. And I'll talk about that in a second. But this is essentially what exponential functions are. Is the pattern that's happening is to get from one y value to the exact next one up. You multiply by the same number each time. And that's kind of the point, is that exponential functions have this constant factor. So just like we could figure out whether a data set was linear by finding if it had a constant slope, you can find if a data set is exponential by seeing if it has this constant factor. And what you're going to do to find that factor is you're going to take these ratios. Now, the ratios we found here were for consecutive years. So they were for x values that were, just 1 apart. What if you're trying to figure out if data is exponential and you don't have consecutive x values, or in this case, consecutive years? So we still can find this factor. So let me write x value here to also clarify that this is generically as well. So what if we didn't have consecutive x values, but we still needed to find whether or not there had, excuse me, we don't have consecutive x values, but we still want to find that constant factor or see if it has that constant factor. How can we do that? Well, it's possible, but it gets a little, if I'm honest, a little gross. But here's how you'll do it. You'll calculate the change in the x value. So you'll take x sub 2 minus x sub 1. I suggest x sub 2 be greater than x sub 1. It just makes the algebra nicer. It still will work the other way, but the algebra is going to be a lot grosser. Well, algebra if you were to do it by hand, I guess. In fact, I'm not entirely sure. Let me check something super duper quick before I say something I shouldn't. Oh, no, that worked. Okay, cool. So yeah, even if you take x1 larger than x2, it'll still work. It just makes it a little grosser if you do it by hand. If you punch it into a calculator, the calculator can do it. But anyway, I just suggest taking the larger x value first. And then what you're gonna you're going to find the factor. Maybe I should say the possible factor, because you have to check multiple cases to see if the factor is the same. And the way you're going to do this is you're going to take the change in xth root of the ratio of the y values. And I'll do an example with both of the year numbers and this easier example in a second. So if you're curious as to what the heck I'm trying to say by that, I'll do an example in a second. Also, in terms of typing it into a calculator, you do have a root button in your calculator. It's usually just that you have to go into a different, not mode, but you have to press one button and then you have to find it, and then you can also write roots in the calculator as a fractional exponent. So for example, if you wanted to take the fourth root of 16, you could type it in as 16 to the 1/4 power and it would do the same thing. I usually just always do this, but you do have a root button in your calculator. If you have a TI-83 or 84, I think it's, yeah, it usually blurs it out. I don't know why it doesn't, it's really smart that it doesn't blur me, but it blurs the calculator. Anyway, you'd have to hit the math button first, and that's what I mean by like you have to go into something and then find it. So there is a root button if you hit math 5. If you have a different type of calculator, I might know, or you might just have to Google. But honestly, I think doing the fractional exponent is a bit easier, but whatever floats your boat. But that math 5 is how you would get it on a TI-84 or 85. And so that number, that's a little gross, will be that possible factor. So let's look at some examples of those. So say I go back to this year example, and I say I go between 2007 to 2009. Well, that means my change in x is 2, right? The difference between 2009 and 2007 is 2. So then what I'd be finding is I'd be finding the square root of the population in 2009, so 15.098 divided by the population in 2007, which does come out to be approximately 1.029866603, but again, up to those 4 decimal places is the same as what we were finding before. And just to push it a little farther, to show it again, so also note, in case algebra is far away from your brain at the moment, usually when you do a root, you have like a little baby number in front of the root to tell you what root to take. If the root would be 2, then that just doesn't need to be written because the square root is just the square root. But say I wanted to go from 2008 to 2012. Well, that means my change in x is 4. I need to slow down a little bit. I always go too fast when I teach to a screen. So that means we want to take the 4th root of the population in 2012 divided by the population in 2008, 14.660. And this would be approximately 1.029860154. But again, to those 4 decimal places is the same number. So what is all this hoopla we've done up to this point? All I'm saying is if we want to find if something is exponential, if a data set is exponential, we're looking for this constant factor. If you have consecutive x values, you can just divide the 2 numbers. But if you don't have consecutive x values, you have to do this kind of root idea. But if those numbers match up at least to 3 decimal places, then you'll say that it's exponential. So going back to this one really quick. So like this one was kind of easier to see that we were multiplying by 2 each time, but then from 4 to 6, it doesn't look like we multiply by 2, but that's because there's a gap between 4 and 6. But if we take the square root of 64 over 16, because we're taking the square root because 6 minus 4 is 2, well, 64 divided by 16 is 4. So the square root of 4 is 2, which matches with the number that we thought we were multiplying the y values by. So hopefully between those two examples, the one somewhat gross and the other one that's a bit easier to see, hopefully that makes sense. Questions before I move on to some definitions? Okay. I'll try to leave some of that in. There we go. So we say that p is an exponential function of t with base a. It can be written like this: p equals p naught a to the t. So p naught is called the initial condition. It's lagging. Pretty bad, apparently. Come on. Whoa. No. Hello. Screen. How about I unshare and reshare? My internet is still up. Okay, let's try this. Unshare, reshare. There we go. Initial condition. So P naught is the initial condition, which can also be thought of as when t equals 0, or maybe not. There we go. Goodness, why is it so bad? My internet is, yeah, no, okay. All right, just if I'm not realizing that it's lagging, just yell at me in chatter. Come off mute. So anyway, P naught is the initial condition, and A, while it's called the base, what it actually represents is A is the factor that P changes by when T increases by 1. So this is essentially what we found in the above. So the 1.0298 is the A value. So these ratios that you take get the A value. Can you see stuff now, Jack? Still nothing? Jack, try hanging up the call and coming back into it. Let me know when you're back in, and I might have to share it one more time. Hopefully that'll work. And can see. Okay, great. Awesome. Good. Where was I? A values. So when you're doing these ratios and any of the root hoopla that we were doing above to find that 1.0298, that becomes your A value. So that's kind of important. Now we also have some classifications for exponential functions, and it kind of depends on what the value of A is. So if A is greater than 1, we're going to have what's called exponential growth. That doesn't look like an R. Let me rewrite that. Growth. If A is between 0 and 1, we have exponential decay. Now there's a couple things to note here. We're not allowing A to be negative. Like there's no, what if A is less than 0? if we had something that looked like this, so -5 to the t, you might say, oh, well, then your a is -5. No, the a value is never negative. That negative would technically kind of be outside the a. It would technically be associated with the p naught, so p naught would be -1. So the a value is never going to be negative. The exponential functions can look like they're negative because we can flip them over and have that negative there. This is a perfectly valid function, but we wouldn't say a is equal to -5. A is never negative. Also, a very important point that I usually forget to mention, but I remembered this time, and I'm going to leave this one up. A is not equal to 1. Notice there's no option for that either, because if this were the case, say you're looking at a set of data and you start taking these ratios and they all come out to be 1, this would actually mean it's linear. And I know that actually comes up in your homework, I believe. There's like a question with a bunch of tables, and one of them would have a being 1. And most of the time people are like, oh, well, then it's exponential because it's constant. If your a value would be 1, it's linear. So it has to be something not 0, not negative, and not 1. So now the other important piece, and I know this is a lot to take in at once. I know this is a lot of different definitions. A is also equal to 1 plus r. Now r is going to be the decimal representation of a percent change. So a lot of times you'll see questions that say like a population increased by 4%, the material is decaying by 4%. I think I used 4% both of those. But anyway, a lot of times you'll be given a percent in these, especially the word problems when it comes to exponential functions. And whenever you're given a percent or a rate, so those two words, and I'll stress that in one of the next examples, that gives you your r value. So I know we did this, all this hoopla up above about finding a and how to find a, and a is the factor and a is important. 95% of the time, you're given r instead of a. It's still important to know how to find both, but more often than not, we work with r and find a from r, and you'll see what I mean when we get to some examples in a second. And just like with the a value, we can have two different situations for r. R can either be positive, greater than 0, which would mean that we have exponential growth. So essentially these two situations here are the exact same. And if r is negative, so r can be negative, then we have decay. So essentially these two situations are the same once it catches up to me. Go. No. Sorry, distracted. Did it catch up to me yet? No, it hasn't. Hello. Why are you being such a butt today? No? Oh, Lord. Internet is still up, so that's not it. There it is. It was just an arrow. I just wanted the arrow. So all I was saying is those two decay things are the same. The most common base that we're going to work with, so the base again is that a value, but the most common base is actually the number e. So e is equivalent to 2.71828, and technically it goes on forever. I probably should have put an ellipses there, but I forgot. It's kind of like pi. So e is a number, and it's called the natural base. Pretty much all calculators do have an e button. Some of them also have an e to the x button, which like automatically puts you up in the exponent. But even if you don't have an e to the x button, you should have a e button. So I know that was a lot of information at once, so let's start going over a couple examples of this. So, boink, boink, boink. The amount of adrenaline in the body can change rapidly. Suppose the initial amount is 15 milligrams. Find a formula for A, the amount of milligrams at time t, minutes later, if A is a couple different things. Now I know that this section is about exponential functions, but those first two, A and B, are actually not exponential. So the first thing we have is that A is increasing by 0.4 milligrams per minute. Now I'm going to say one thing, and then I'm going to slightly backtrack and yet not backtrack, and you'll see what I mean by that in a minute. If you see the phrasing, you know, something per something else, this is most likely linear. So since there's nothing else telling us about what's happening besides the phrasing A per B milligrams per minute, this is going to actually be a linear relationship. So here we actually want to find some linear function for this data. So we need essentially the B value and the M value. Well, if you think about the B value, that's the y-intercept. In some contexts, like this one, since we're talking about time, in some contexts, the y-intercept can also be thought of as the starting point, because if you think about it, you can't have negative time. So since time would start at 0, that means the function will start wherever the y-intercept is. So in some contexts, you can think of it as a starting point. So that means that our B value is going to be 15 milligrams, because that was the initial amount that was administered, or that's in the body, I guess. And then the slope, well, that's essentially what we're told here. It's increasing by 0.4 milligrams per minute. So that means our slope's going to be 0.4. So the equation I'm looking for here is 0.4t plus 15. And then in part B, the only thing that's different now is that it says decreasing instead of increasing. Now that doesn't change where we've started at all. We're still starting with 15 milligrams. Once it catches up, oh jeez. Why? Why is it cranky today? Of all days. I'll just keep unsharing and resharing. And as always, if you can't see it at any time, just let me know. So that doesn't change where we started. So the point was that B is still 15. But by saying decreasing, that changes our slope. Oh, don't immediately lag. Oh, what is happening? All right, I'm going to try this then. So I guess I have to stop the recording really quick and then do another one.